Okay, thanks for coming. Let's go ahead and get started. So this is section 15.1. It is double integrals over rectangular regions. So I'm going to start off with an idea of what this is about. Let's go back to what is an integral really. And so I'm going to use an example I found, which is that farm soil contains 5% nitrogen, or at least it should. So let's say this rectangle R here is 10,000 kilograms of soil, and we want to know how much nitrogen. Now, of course, we'd like it to be 5%, so if we did 0.05 times that, we get 500. But let's say we're not sure. We're checking to see if it's accurate. Well, you could plow up the whole field and weigh it all, but that would take a lot of work. So more likely you will pick a single point here and sample it. You'll pull up a tiny bit of soil from here and weigh it and figure out how much nitrogen is. And so say we do that and we get 4.8%. Well, in that case, the total amount would be 0.048 times 10,000, or 480 kilograms. Simple enough. Now, how would we get a better estimate? Because it might be that this one piece is really not representative. So I paused there for you to answer a rhetorical question, and hopefully most of you said, well, we'll take more samples. So let's split this up into 4 equal regions. R1, R2, R3, and R4. And so we will take a sample from each one and measure that. Let's say this sample is 4.9%. You notice I'm taking samples from the middle of each patch. It's not required, but it is a common way to do it. It's called midpoint. I'll go over that in a little. And let's say these are the results we get from each spot we take. That looks like a decimal. It shouldn't be there, so let's erase it. So we took a sample from each of these 4 patches, and that was the percentage we got. So if we want to know how much nitrogen is, well, we'll multiply each one 0.049 times the amount of soil in that entire first rectangle. Assuming these are evenly sized, which we really want to try to do, it'd be 2,500 kilograms in each one. And then we'd have 0.051 times 2,500 there, plus 0.052 times 2,500, plus 0.06 times 2,500. And that equals out to, you can factor 2,500 out if you like and just add the decimals up, 530 kilograms, which is a little higher than the 500. Our first estimate was a little lower. But the idea is that some our estimates will be too high, some our estimates will be too low. But if subdivision might be 2, 3, 4. It's 5 columns and 2 rows. a lot of times we'll represent it as m cross n, meaning the number of rows or the number of, I think this would be 5 by 2 would be the size, but we'll go over that as we go on. So we'd have R1, R2, R3, R4. Honestly, I don't really care that much what order you write them in, but so on. And so what we would do in each one of these, we would take a sample and we multiply it by, in this case, 1,000, because there are 10 patches. So we will have 1,000 total in each one. So let's work out the notation for this then. Erase that. So we're going to say delta AI is the amount of the soil in each block. The total amount. And the reason why I'm using A is because it's just based on the area. We're assuming this is evenly the same depth everywhere, so each block have the same area and they're also have the same volume. We'll say x sub I, y sub I is a point in Ri, and we'll say f of xy gives the nitrogen content at the point xy. So it's a function of two variables over a rectangle. The reason why this is so versatile is because it doesn't have to be soil, and it can be literally anything if we can divide it up into rectangle and measure something at every part. So if you think about what we've been doing, how we would generalize this, then we would say I'll call it V. Well, we've been estimating by saying f of x1 comma y1 times delta A1. Okay, and f is the percentage, not total amount, yeah. Plus f of x2 y2 times delta A2 plus dot 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 plus f of x10 y10 times delta A10. And this is factorable because if we make a point of making all the A's be the same size, which we generally will want to do, it would just become the sum from I equals 1 to 10 of f of xi, yi, delta ai. So that's how we do an estimate. And in a practical setting, oftentimes that's what you have to do. You won't know what the function f is, so you just pick points from each spot and measure it directly, and then try to estimate based on that. And the degree of estimate has to depend on how much precision you want. But the true V, the true amount, we have this idea that if I keep increasing the number of plots I pick from, the number of samples, I should get more and more accuracy, more and more precision. And so, as is standard in calculus, we will describe this as a limit. Take the limit as n goes to infinity of the sum from I equals 1 to n of f of xi, yi delta AI. And this is going to define what we call a double integral. And if you're wondering why it's V, it's because most commonly this is used with volume. So if it were z equals f of xy, z is the height off of the xy plane, this would use to give you volume, or an estimate of volume. Well, and then once you take the limit, it will become the exact volume. Or rather, if integrals work on it, then this will give you the exact volume. There are some surfaces that are really jagged in such a way that the integrals can't really be done, but that's not something we deal with in this class. Let me describe it precisely then. So we're going to define the double integral here. So if we've got some surface, some domain, I guess, that's a rectangle, and we divide it up as a bunch of sub-rectangles, and I'm not going to spend the time checking to make sure these lines are exactly straight, but imagine they are. Or that they're exactly the same size. Again, just bear with me. Let's not even draw them all. Let's just say, because I don't want to give the impression that it's a specific number. I'm thinking there's a whole bunch of ones here. And we'll label these as x1, x2, ... xn. And then y1, y2, ... ym. And so you can imagine this thing is this. There's m column or m rows and n columns. So the total number of blocks is n times m. So we're going to define a double integral. And again, if we think of the f as representing height, then this is the same as volume. But it can be used for summing up anything that varies well, not even smoothly, but that varies over a rectangle here. So we'll say the double integral over r, where r is this entire rectangle, f of x, y, dA. dA represents a tiny piece of area. So we've got some little tiny piece. Now, I'm not even that's too big, we keep making it smaller and smaller. It is the same as the limit. If we take both m and n to infinity, the sum from I equals 1 to n, the sum from j equals 1 to m, f of xij star yij star times delta A. Okay, let's spell out what this means. The delta A thing, we would say delta AI if they were all different sizes, and technically we would be allowed to make them all different sizes, but it's easier calculation-wise to make them all the same. So in this class, we're going to assume that all the boxes are the same size. What is the ij star, and what's that about? Well, the idea is that xij and yij are corners. We don't necessarily want to take from the corners. So we say this is a point in the rectangle xi minus 1, comma, xi cross yj minus 1, yj. Now in a real analysis or measure theory course, they'd be really picky about making sure you keep track of which I and which J is what. And we're not too picky about that in this class. The reason being because we're not often going to do this by just this brute force calculation method. More often, we are going to use some calculus techniques to skip over this tedious summation. But we say if this limit exists, then the f is integrable. F is integrable over R, provided that limit exists. So when we're going to infinity, there's no rule about how you pick these points. Any point will do. But we are going to have some standard methods of picking. So let's, I'm going to clear the screen now. Pause if you need to keep copying. So the shorter way to write this would just be say v is the double integral r f of x, y, dA. Oh, it's not the shorter way. I already wrote that earlier. But that's what it means. It means that we divide up the xy plane into rectangles. We take a sample from each one, and we essentially get a tower. You can look this in your book. In fact, I would recommend it right now. There's a picture of little, sort of a block tower. The idea being like, here's our domain, and so we have like one little block here. I'm sorry, I'm doing this on the fly. I didn't, should have, yeah, if we got a domain here, so we'll have this, dot, 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 up to here. Boy, this is bad drawing. Well, we get a little tower there. Then at another point, we get another little tower that's maybe not quite as high. Then another tower, another block, we get a different size tower. Like I said, the book has a better illustration that I would advise looking at, but basically it's saying at each point we figure out, or at each block on the xy plane, let's say this is x and this is y, we would, for each block, we would pick one height and say, like, that's the height across that entire block. And we can easily calculate volume. It's the area of the base times the height, because we make the height constant. And then the smaller the blocks are, the more accurate our estimate becomes. All right, so let's do some examples of how we're going to do this. All right. So, example 1 here. Estimate volume of the solid above the square 0, 2 cross 0, 2 and below z equals 16 minus x squared minus 2y squared. Now you could try to draw this thing. I think it would be a paraboloid. Yeah, I think it would be a paraboloid. But we don't really need to here. I would draw the box, the domain here. This is 0, 2 cross 0, 2. So let's say 4 squares, m and n are both 2. So this will be used in the book to say how much to divide it up by. So the y's are m and the x's are n. At least that's how I I think that's how they have it. I'm pretty sure that's okay. You can always look it up if you need to. So let us do. So what are the area of each of these? Okay, 0, 1, 2, 1, 2. All right, so I am going to say, let's use upper right corners. So like I said earlier, there is no really absolute rule about how to pick points from each region. That said, it's usually a good idea to space them out a bit. So you wouldn't want to pick them all really close to each other. So we typically have either we all pick from the same corner or we pick from the midpoint. So let's do it this way. We'll have 1, 1, 1, 2, 2, 1, and 2, 2. So we get f of 1, 1 plus f of 1, 2 plus f of 2, 1 plus f of 2, 2. And all that times delta A, there are 4, the total area is 4, and it's divided evenly into 4 pieces, so I guess that's the area is 1. So then we would plug each of these numbers into this function here, this one, to get what the f or z values are. So that would give us 16 minus 1 minus 2 would be 13, plus plug in 1 for x and 2 for y. That'll give us 7. Again, 2 for x and 1 for y gives 10. And plug in 2 for both numbers gives 4. So it's 34. So that's the upper right rule. Now on the other hand, it might ask you the midpoint rule. So if that's the case, your test points would be 1 half, 1 half, 1 half, 3 halves, because it's halfway between 0 and 1 is 0.5. Halfway between 1 and 2 is 1.5. And same for the x is 0.5 and 1.5. 3 halves, 3 halves, 1 half, 3 halves, 3 halves. And so it'd be the same thing. You would just plug in each pair of points into this. And I'm not going to do that for you. But you can do that on your own if you need to. But, what the heck. All right, let's do this here. 16 minus 1/4 minus 1 half. If I plug in 1 half to both of those, I get 1/4. 2 times 1/4, so I'd get 15.25 plus 16 minus 0.5 squared minus 2 times 1.5 squared, which gives me 11.25, plus, let's see, 16 minus 1.5 squared minus 2 times 0.5 squared is 13.25. And then the last, let's make them both be 1.5. 9.25. Then add those together. 15.25 plus 11.25 plus 13.25 plus 9.25 gives us 49. So that top right rule gave 34. This midpoint rule gave 49. We might also do the bottom left rule, and that would probably give something different entirely. I would guess it'd be, well, I don't know what it would be, but we would do 0, 1, 0, 0, 1, 0, and 1, 1. and that would give us another estimate. And these estimates are all different, but the reason why they're so different is because we only have 4 boxes. If we made a lot more boxes, the estimates would be closer. The idea is that if we keep taking more and more boxes, they'll get closer and closer together, and they'll all sort of meet up at the real volume. Okay, so I want to now see how we can transfer this into calculus. Because right now we're only defining integrals based on sums, and that is how they're defined, but actually working them out as antiderivatives is a more common thing we like to do in calculus. So we're going to make that connection. The reason why it's good to go through all that trouble is because you start to recognize that anytime you're splitting something up as taking estimates over a bunch of subdivisions, then it becomes an integral problem. But yeah, so let's say we've got a whole bunch of these again. All right. And so on and so forth. And then we got a whole bunch of y's here as well. All right, so I want to pick this one particular one. Let's focus in on just one little strip here. This is xi, and this is xi plus 1. And the y's will go up all the way to ym. So this top thing is y sub m. This bottom one is y sub 0. So what I want to know is just what is the volume over xi plus 1. Meaning if I could get this entire strip here and get the volume right there, what would it be? All right, so let's see if we can do this using our integral idea. Well, the idea is that at this point, if this is we'll pick a point somewhere between xi and xi plus 1. So we called it before, I think we called it xij star for each point here. Here is yj, here is yj plus 1. Those two lines, or those two, yeah. And so the point there, the red dot, is xij star yij star. It's a specific point in the box there where the x is between I and I plus 1, the y is between j and j plus 1. So we'd say, if we're just doing this one strip, well, the x is pretty much the same every time. It's going to be the same xij each time. So we'll just have to say, let's see, let's call it delta v, the piece of volume on this vertical strip. Well, we would simply say we'll take f at xij star yij star times delta aij, the area of that box. Now, I is just I. I, for the xi, is going to be the same the whole way up, the same x value the whole way. But j needs to range across all its possible values. So we will take the sum from j equals 1 to m. That is the delta v. But now we can take a limit to make it exact. The actual volume over there, let me move this a little. We will put in the limit as m to infinity. All right, so this gives us how we would add up the actual volume along that strip. But notice that j is the only variable now. I is going to be the same, xi is going to be the same for all of them. So this is the same as saying, let me add in a little label here. I'll call this A to B, and this y naught can be C to D. So we can rewrite this whole rectangle as A, B, cross CD. Okay, well, we are summing over each piece. We are multiplying by its area, and then we're taking the limit to infinity. Well, this allows us to use the fundamental theorem of calculus from Calculus 1. This is the integral from C to D of f of xi y dy. Now let me stop for a second and let's think about what this means. We have two variables here, xi and y. But the y is one associated with the little d here. This is because y is the thing we're integrating over. It's changing. X is not changing. So if we work this out, the x, we would plug in the same number for x every time. This is not even really a function of x then, because right now the x is held constant. It's only the y that's changing. We might call this vi. So that gives us the volume of the first strip, or that ith strip, I guess. But now we say, well, what if we go across all the other strips? Well, then that would, as we take the limit, become the integral over x. So let's write this out. The volume is the limit as m and n both go to infinity of the sum from j goes from 1 to m and I goes from 1 to n, f of xij star yij star delta aij. Well, let's separate these out. Let's do everything to do with the y first, like we just did. So we'll say, let's see, y was the j, the way we counted was I represented the x and j represented the y, right? Yeah, because we can see at the top the y goes from 0 to m, and here we have j goes from 1 to m, so the j is the one associated with the y. So we'll pull out all the other things. So we'll pull out limit as n goes to infinity of the sum from I equals 1 to n of parentheses. Limit m goes to infinity sum from j equals 1 to m of f of xij star yij star delta aij. Well, now that inner one, we've just defined it. It becomes, let's see, limit as n goes to infinity, sum of I equals 1 to n of integral from C to D f of xi comma y dy, and we'll say delta vi. And the reason I'm now using vi is because it's the volume of the ith strip instead of an area like it was before. Before, we were integrating over areas. But now each vertical strip has a volume that we've theoretically computed. So we're going to multiply times the volume at each stage. And so then this says we go left to right, we pick one point in the x between xi and xi plus 1. We pick 1 point and then calculate the volume of the entire strip. Do that for every horizontal strip. Multiply to get the volume, or integrate to get the volume. Then add those up. Well, that becomes another integral. See, we have another limit of a sum here. So that then becomes the integral from a to b of the integral from c to d f of x, y, dy, dx. This is called an iterated integral. All right, so that's a lot of theory we just did, and it's not something that you're going to be expected to reproduce at will. This is the sort of thing you would do a lot of in, like I said, a real analysis or a measure theory, where you would go into how integrals work more generally. But we want to do this in a practical way for smooth functions where the rules for integrals are not as complicated. So all that theory was to tell us that we can do the first integral. We hold x fixed. We treat it as a constant, and do the integral with y as the variable. Get rid of y because it's a definite integral. Then we don't have y's left. We just got rid of them, replaced them with c and d. Then we do the integral for x. So that's the key to this subject, is we're going to have multiple integrals, 2 or more, and we work them sort of from the inside out. So let's do an example. This is a practical example here. Or at least, I don't know what I mean by practical. It's one that you could actually work out explicitly. Explicit example, maybe that's what I meant to say. Okay, x squared y dy dx. So the first variable is dy. If it helps, you can put parentheses around here, because the key is the inner integral matches the inner limit, the variable. So y goes from 1 to 2, but x goes from 0 to 3. Outer to outer, inner to inner. All right, so we say, okay, we need to do an antiderivative with respect to y, meaning x is constant. This is the same as the partial derivatives in reverse here. So 0, 3, so we go, all right, y equals 1 to y equals 2. I often do this. Instead of just writing 1 and 2, I'll write y equals 1 and y equals 2, just so I don't forget which variable I'm plugging in for. X squared is constant, and the integral of y squared would be y squared over 2. And then dx is still out there. So now we say this becomes 0 to 3 of, let's plug in 2 for y, so it'll give us 2 squared is 4x squared over 2, minus, now we plug in 1 for y, x squared over 2 dx, which becomes, okay, 0, 3 of, I guess that would be 3 halves x squared dx. And then we integrate this one. It becomes 0 to 3 of, let's see, raise the exponent 1, so it become 1/2 x to the third. And then we will plug in 3 for x and 0 for y. 1/2, 27 minus 0 is 27 over 2. Okay. Okay, so make sure you follow that. Let's try, you know what if we did the opposite order? Let's try the same problem, but reverse the order. So we'll go 1 to 2, 0 to 3 of x squared y dx dy. So it's still x goes from 0 to 3 and y goes from 1 to 2, just doing it in the opposite order. 1 to 2, x equals 0 to x equals 3 of, okay, if we do the x integral, it would be x cubed over 3. So we'll get x cubed y over 3. Because again, y is being held constant. So just like with derivatives, we just sort of leave it there as a multiple. This becomes, excuse me, let's not lose my outer limit, dy. So it goes 1 to 2 of 27y over 3 minus 0 over 3 dy. So that's 1 to 2 of 9y dy, which then becomes 1 to 2 of 9 halves y squared, or 9 halves 2 squared minus 1 squared. That's 9 halves times 3, which is 27 over 2. Good, it gave the same answer. And, I mean, it seems like it should, because we defined this in a way so that we did integrate along y first and then along x, but we could have done it the other way and it shouldn't have mattered. And I played a little trick there when I was showing the derivation when I used the fundamental theorem of calculus, which only really works for continuous functions. But because of that, that means if we are continuous, we can guarantee it will work and the order won't matter. And so this is called Fubini's theorem. Also sometimes called Fubini-Tonelli, two Italian guys who worked on it together, I guess, or maybe not together, I'm not sure. I'd have to look that up, how it worked. But if f is continuous on r equals AB cross CD, then double integral of r across r of fxy dx dy, you could write it as you could go along the x, so x would go from a to b, and then along the y, that's c to d, or dy dx, on the y from c to d, and the x from a to b. So the actual definition of the integral is that thing about taking samples from each point in each from a point in each rectangle and multiplying by the area, and then taking the limit as the number of rectangles goes to infinity. But as long as f is continuous, we are allowed to split it up and do it as an iterated integral where we do one variable at a time. There's actually, this is the simple version of Fubini's theorem, because again, like I said, we stick with continuous functions here. So there's a more complicated one for those of you who are interested in measure theory is part of analysis 3 and 4 at this school. All right, so let's do this. Let's do an example here. Example, double integral x minus 3y squared along a region R, which I will give you a picture here. So let's say this is 0, 1 to 2, 1 to 2, 0, 2. And I'll just say the quiz is probably going to be one of these iterated integral problems you'll have to work out. The homework for this section is up, so if you want to if you do all of 15.1, you'll homework. You'll be well prepared for a quiz. Okay, so we really get to choose what order we do. So I'm going to do x first. X minus 3y squared dx dy. X goes from 0 to 2, and y goes from 1 to 2. We're only dealing with rectangles today, because more complicated regions we can do, but that's for next section. So, x will go from 0 to 2. So now we need to do the x integral. So I say, first term is x, so its antiderivative is x squared over 2. Next term is 3y squared. Now, be careful with this one. 3y squared is a constant. If you'll remember, the integral of a constant is just that constant times x. So this integral, or antiderivative, is 3x y squared. Now we still got dy. So again, it's the same thing as with partial derivatives. We got to be careful that when we're dealing with one variable, in this case x, the other variables we just treat as though they're regular constant numbers. All right, so this becomes 1 to 2 of, let's see, 4 over 2, that's 2 squared over 2, minus 3 times 2 times y squared, minus, if I plug in 0 for the x's, I'll get 0 dy. So this is 1 to 2 of 2 minus 6y squared dy. Which then, this is a regular calculus 1 integral, 1 to 2 of 2y minus 2y cubed. Now, I'm not bothering with the y equals because there's only one variable now. 2 times 2 minus 2 times 2 cubed minus 2 times 1 minus 2 times 1 cubed. And then just crunch those numbers out. 4 minus 16 minus 2 minus 2 is negative 12. So what does it mean for it to be negative? Well, if we're thinking of it as volume, it means the xy plane is the floor. We've got the volume is mostly under the floor. So if it was like a big bomb shelter dug out underground, we would consider that to have a negative volume. This might have some positive and some negative, but the net amount is 12 more below ground than above ground. All right, so let's do some more examples. I'll roll through a few examples here. We're past the worst of it, the theory part. Now we just have to practice. I don't know if that's fair to say theory is the worst part. It's the part that most calculus students would rather not spend too much time on. Okay. And R is going to be 1, 2, cross 0, pi. So I could give you the region in coordinate form like this, or I could draw a picture. It amounts to the same thing. Okay, so I went to do this, and I said 1 to 2 and 0 to pi of y sine xy dy dx. So I look at this, and I say, okay, y is the variable I'm doing first. Here, I've got a y in here, but I've also got a y out here. How do I... And I'm thinking, ooh, back to calculus 2. This looks like an integration by parts problem. I've got a y multiple out front that's multiplied by something else with y in it, so I probably have to... I don't want to do integration by parts. So I'll tell you what, instead, let's switch the order. And we do this because this function is continuous everywhere. Y sine of xy dx dy. Okay, now in this case, I can just factor that y out. Because this dx, this is with respect to x, meaning y is a constant, so I can just pull it out altogether. 0 pi of y, 1 to 2 of sine xy dx dy. Okay, what comes next? This inner part here, how do we integrate that? Well, we can do it as a u sub, although sometimes you don't have to write out necessarily, but we'll do it. We'll write it out this time. If u is xy, then du. Now dx is a variable, so du over dx, or really, I suppose it's del u over del x in this case. It's partial derivatives. The x derivative of xy would be y. So du equals y dx. Oh, maybe we shouldn't have factored it out. Maybe we should have left that y in there, because then it and the dx can combine to make du. So we go from 0 to pi of integral of, okay, sine of u du. And then there's a dy over here. Now what does u do? Okay, let's think about this. X here, x goes from 1 to 2. So if I plug in 1 for x, I get y. If I plug in 2 for x, I get 2y. And I'm going to double check my notes just to make sure that I'm doing all this right. 2y to y, yeah. Okay, so now at this point, it's not anything particularly tricky. It's just we have to run through the pattern. All right, so you'll notice what I'm saying here is u is now a dummy variable. It's going to be replaced with y's, which will then be replaced with constants. The idea with these integrals is that each time you do it, one variable should disappear, be replaced by either constants or something with the other variable that we still have. And so your limits should only be in terms of the next variable out. So anyway, 0 pi goes from u equals y to u equals 2y of antiderivative sign is negative cosine of u, and then dy out here. Excuse me. Then becomes integral from 0 to pi of negative cosine 2y plus cosine of y dy. Because you plug in 2y and you plug in y and you subtract them, negative, negative becomes positive. And now, just some good old calculus 1 integrals. 0 to pi of negative 1/2 sine 2y plus sine y, which becomes negative 1/2 sine of 2 pi plus sine of pi, bracket, minus, I always use brackets for these for two separate pieces, negative 1/2 sine of 0 plus sine of 0. Well, sine of any multiple of whole number multiplied by 0, so this whole thing comes out to 0. Okay, so that is how that example works. All right, we're going to keep going. Right, so let's do a few more examples. All right, example. Find the volume of the solid bounded by the elliptic paraboloid x squared plus 2y squared plus z equals 16. The planes x equals 2, y equals 2, and the three coordinate planes. That's x is 0, y is 0, z is 0. XY plane, XZ plane, YZ plane. Yeah, I think I said all of them. Okay, so this one might require a little drawing. It probably doesn't need it, but I'm going to draw a little just to give an idea. How do we find the volume? Well, the formula here, that volume over a 2D space R is the same as the double integral over R of the function 1 dx dy. Or no, wait, hold on. Am I saying this right? Let me back up. No, sorry. A function of f of xy dx dy. Yeah, we said that already. I was getting ahead of myself. I was thinking of a theorem from another chapter, but let's not worry about that right now. All right, so this equation, x squared plus 2y squared plus z equals 16, that can be rewritten as z equals 16 minus x squared minus 2y squared. And so this would start at a height of 16 and sort of loop down to where, let's see, if y is 0, then x would be 4. So 4, 0, 0. If x is 0, then y would be 2 root 2. Right? Yeah, 2 root 2 or root 8. Yeah. It's 0, root 8, 0. And then we also have the planes x is 2 and y is 2. So that would really just cut our base here. Instead of being this entire sort of, I don't know, semi or elliptical region here, we're just going to do a square. If we want to do the whole region, well, that's for next unit. So it says x is 2, y is 2, and the coordinate plane is x 0, y is 0. So that means our r, we'll call r to be the rectangle on the xy plane that we're integrating over, 0 to squared. And by squared, I just mean the x goes from 0 to 2 and the y also goes from 0 to 2. So it makes a square. So let's integrate. Okay, so yeah, f of x, y is z. That's what I was trying to say earlier, and I stumbled upon my words a bit. But we're going from a floor where z equals 0 to a ceiling where z equals 16 minus x squared minus 2y squared. Since the ceiling is variable, we have to use the integral to add up all across all the different parts of the region. So what we do in this example, and other examples like it, is we rewrite the ceiling to be z equals such and such, and then we integrate from 0 to that ceiling. So this could be rewritten as double integral across r of z dx dy. Yeah. Okay. So what we have here is the double integral of z dx dy, where x and y both go from 0 to 2. So instead of z, let's replace it with double integral from 0 to 2 of 16 minus x squared minus 2y squared dx dy. And if you want to do dy, then dx, it'll give you the same thing. So this becomes, let's do the x integral first. We get x is 0 to x is 2 of 16x minus x cubed over 3 minus 2xy squared. No, that's it. 2xy squared. See, I was about to do some other thing because of the y there, but x is the variable right now. So since there's no x in it, we just multiply 1 on. And now we replace all the x's with 2 or 0 and subtract. Everything's got an x, so the 0 part will disappear, so it'll become 32 minus 8 over 3 minus 4y squared dy. And then we do another one of these, so we get 0 to 2 of 32y minus 8 thirds y. And you could combine these right now if you wanted to. It doesn't really matter. Minus 4 thirds y to the third, which would become 64 minus 16 over 3 minus 2 cubed is 8, so that's 32 over 3. And then that's, so what do we got here? 64 times 3 is 192. So 192 over 3 minus 48 over 3, which becomes 144 over 3, or 48. That's the answer. Okay, now there is one more thing that I want to do. I want to give you a theorem that can speed some of these up. So, theorem. If f of xy can be written as g of x times h of y, and we're on the rectangle AB cross CD, then the double integral fxy dA across R, it could be written as that we get, well, I'm going to just draw out the in-between step as sort of a proof because it's actually really not very complicated. If you have f of x, or sorry, let's replace it. G of x, h of y, dx, dy, where x goes from a to b, y goes from c to d, that the y part can be pulled out of here entirely. So we'll get c to d of h of y dy and a to b of g of x dx. Or you can write them in the other order. The point is that if you can factor these so that one factor only has x and the other factor only has y, then you can just split into two separate integrals and multiply them. And that can often make it easier because you don't have to worry about like, oh, is this a constant or is this a constant kind of thing. So let me show an example there. Here we go. So let's see, an example here is r is going to be 0 to pi halves squared. And let's say we want to integrate sine of x cosine of y dA. Well, since this part is only x and this part is only y, we can just do it like this. Sine x dx from 0 to pi halves. And from 0 to pi halves, cosine y dy. Which then becomes 0 to pi halves negative cosine x, 0 to pi halves sine y, which is then negative cosine pi halves minus negative cosine 0 times sine of pi halves minus sine 0. And then, our trig, cosine of pi halves is 0, sine of 0 is 0, so we get 1 times 1 is 1. This could have applied to one of our earlier examples, by the way. For instance, let's say we could not use it for one like this, x minus 3y squared. These are two functions, they're subtracted. They're not multiplied together, so there would be no way to split this one. You would have to do first dx and then dy, or vice versa. But on the other hand, the earlier example we had where it was double integral of x squared y dy dx, where y went from 1 to 2 and x went from 0 to 3. Since this is split into an x factor and a y factor, we can separate this completely as 0 to 3, that is dx is with the 0, 3, so it'd be x squared dx. Then the y part would be 1 to 2 y dy. And then we could just do these separately as 0 to 3 of x cubed over 3, 1 to 2 of y squared over 2 becomes 27 over 3 minus 0 times 4 over 2 minus 1 over 2, which is 9 times 3 halves, or 27 halves, which is the same we got last time. All right, and that does it. So enjoy spring break. Or if this is Sunday night or Monday right before class, I hope you already did enjoy your spring break. And I will see you later. Bye-bye.